Our mission in this deep dive is to explore how established paradigms are being shaken up and redefined across biology, physics, and neuroscience. We've pulled sources from orthopedic surgeons, cutting-edge physicists, pioneering neuroscientists, and even actually a legend in microprocessor technology. Get ready to uncover some truly surprising nuggets of knowledge that reveal just how much we're still learning about concepts we often take for granted.
Okay, let's unpack this, starting with something you use every single day, your own body. For centuries, going way back to a fellow named Pirelli in 1680, the traditional model of biomechanics has viewed the body as like a series of rigid levers, almost like building blocks stacked on top of block.
Right. And that model, while it seems intuitive on the surface, it leads to some pretty counterintuitive physics when you really look closely. Take standing on your toes, for example. Classic mechanics would describe that as a third-class lever. Now imagine trying to lift a heavy weight with a crowbar, but you put the fulcrum between your hand and the weight. It's incredibly inefficient. That's the problem this old model presents for something as common as just standing up on your toes. Gravity should actually pull you down as your calf muscles contract, and those tiny muscles in your foot. They'd be, well, laughably insufficient to lift you off the ground in that traditional lever system.
It really makes you question what's actually going on, doesn't
Yeah.
it? This old lever model also struggles with things like a dinosaur's incredibly long, flexible, yet stable 10-meter neck, which could have, 16 vertebrae, like a swan's neck? How does that not just flop over?
Exactly. Or even our own wrist bones. They're sometimes described as a bag of bones with extremely low friction, something like 0.005. How do they not simply collapse or grind apart under weight? It doesn't make sense.
So the calculations based on levers just don't hold up.
No, not really. They often predict muscles tearing and bones crushing under typical loads. It's just not mechanically sound for a living system. Evolution, after all, favors efficiency. And as one of our sources puts it, this rigid model is like a pile of bricks. It simply won't work for dynamic, living structures from a single cell all the way up to, say, a giraffe.
Okay, so if it's not levers and rigid connections, what on earth is it? How does the body achieve this incredible strength, flexibility, and efficiency without tearing itself apart?
Okay, here's where it gets really interesting. The inspiration for this different idea, biotensigrity, actually comes from art, from artist Kenneth Snelson's sculptures, like his piece The Needle in the Hirshhorn Museum. Imagine a structure that's a continuous tension system, where the compression elements, the poles, actually float within a network of tension, almost like a bug caught in a spider web. The poles aren't rigidly connected end to end, they're suspended by the cables.
Wow, so the poles float. That completely flips how I've always pictured bones inside my body. So applying that to biology, how did that translate into, stability, mobility, and function?
It's revolutionary, really. Biotensigrity emphasizes that biological structures are inherently stable because cells are kind of stuck together by spit. That's surface tension between fluid surface cells. They're not connected by bolted hinges that would need to be rigid and would wear out. This allows biological systems to be omnidirectional, functioning right side up or upside down, bending and twisting in any direction without breaking.
That's fascinating. So it's not about fixed, rigid connections, but a dynamic, self-balancing system.
Yeah.
And you mentioned nonlinear behavior. Can you explain that a bit more intuitively? What does it mean for something to initially deform easily but then get stiffer and stiffer under more load? And how does that make things more energy efficient?
Absolutely. Think about how a soccer ball or maybe a golf ball deforms when you hit it. It compresses, absorbs the energy, and then springs back. That's nonlinear behavior. For our bodies, it means that at low loads, our tissues are flexible, allowing fluid movement. But under higher loads, they become incredibly stiff to protect us and transfer force efficiently. This makes biological systems far more energy efficient. One source called it a splashdown effect, like using a piston in a spring for movement. It allows us to store and release elastic energy with minimal muscular effort.
I'm still picturing that breakdancer. It really makes you think about how we perceive movement, doesn't it? So instead of unstable square-frame structures with rigid hinges,
Right, which would collapse easily.
nature favors inherently stable triangulated truss systems, like those you see in truss bridges, like Scotland's Firth of Forth Bridge, which apparently Darcy Thompson observed way back in 1917. You even see this in something as simple as how oranges stack stably in a grocery store display.
And it gets even more specific. Biotensigrity points to polyhedral trusses, especially the icosahedron. That's a 20-sided shape. In these structures, the outer shell is in tension, and the compression elements float internally, never actually touching each other directly. You find icosahedrons everywhere in nature. Viruses, microscopic radiolaria, Volvox algae, dandelions, even pufferfish when they inflate.
Wow.
And even at the cellular level in DNA, collagen, and the internal structure of bone, which apparently forms stacked helices. It's a fundamental pattern.
So in this model, bones aren't pressing on each other. They're hubs floating in a soft tissue network. Can you give us a concrete example of that and what it means for how forces move through our bodies?
Yeah, think of your shoulder blade, the scapula. It basically floats in muscle mass, much like the hub of a bicycle wheel, where the muscles and ligaments act like the tension spokes. The tension from the spokes pulls the hub into place and keeps it stable, rather than something pushing it up from below. So ground reaction force, when you walk or run, isn't localized just to your joints. It's distributed throughout the entire biotensigrity system. This results in, quote, no underfoot shear, which helps explain why our joints don't wear out instantly despite constant use.
It's incredible how this applies to so many different biological functions, from movement to internal organs. Things like soccer balls, golf balls, and you mentioned the heart, alveoli in the lungs, the bladder, bowel, uterus, kidneys. They all behave as nonlinear pumps.
Exactly. They squeeze down and expand out, functioning like these incredible icosahedrons. They change shape efficiently. And what this means for us is that someone like a breakdancer can achieve incredible stability and mobility with flexible joints using less energy and functioning in any orientation, upside down, sideways, whatever. That's a clear advantage over rigid lever systems. Ultimately, biotensigrity offers a comprehensive, systemic model that applies equally well to all living structures, from viruses to vertebrates. So when we understand the body this way, it could completely change how medical professionals might approach injury, pain, or even rehabilitation.
It absolutely challenges what we thought was fundamental about our own bodies.
Yeah.
And speaking of fundamental definitions being challenged, let's turn our attention to something even more basic. What exactly is life? For a long time, defining it has been a real challenge, usually involving criteria like self-sustainment, metabolism, growth, reproduction. Back in the 1940s, Erwin Schrödinger even introduced the idea of a periodic solid containing chemical information, which remarkably predated the discovery of DNA.
Yeah, and viruses have always been the ultimate borderline cases, haven't they? Initially, they were seen as little more than toxic chemicals because of their tiny size and complete dependence on a host. They lack essential metabolic functions on their own. Then Wendell Stanley crystallized the tobacco mosaic virus in 1935, showing they contained biochemicals and DNA. But they were still considered non-living, or at best, living a borrowed life.
But now, we have a new discovery that makes the definition even more mysterious. Sucunarchaeum mirabile, found recently in these organisms called dinoflagellates. It's described as slightly more complex than a virus, but much, much simpler than any bacteria. And it also requires a host for most of its functions. So what makes this specific organism so special?
Well, what makes Sucunarchaeum so special is its incredibly tiny genome, only 238,000 base pairs, which is surprisingly small, even smaller than some viruses. And here's the kicker. It's part of the ancient archaea family, the group of microbes that formed the basis of our own complex cells billions of years ago. This organism represents pure simplicity. It's an extremely specialized organism that has dramatically reduced its genome over time.
So it's a true hybrid. It completely lacks metabolic pathways, just like a virus, meaning it has to steal them from its host.
Yeah.
But crucially, it contains genes for its own DNA replication, things like ribosomes, mRNA, and tRNA. And it can produce its own membrane proteins, which is much more like archaea.
Exactly. It's described as a perfect parasite that gets in, steals metabolic pathways, replicates itself using its own machinery, and then leaves.
So this raises a really groundbreaking question. Is this alive? It's so virus-like in function, yet genetically it's part of archaea, our distant cousin. This entity creates a major problem for biological definitions, blurring those lines in a way that forces us to rethink everything.
Right. Where do you draw the line now?
And when those lines blur so significantly, what are the biggest implications? If viruses or things like this truly evolved from more complex life forms that simplified, does that challenge our entire understanding of evolution, always moving towards greater complexity?
It certainly seems to. This groundbreaking discovery suggests that many viruses might actually have originated from bacteria or archaea that lost their complexity over time. Rather than always being these tiny, primitive entities from the start, it forces us to completely reinterpret how viruses formed and, the very idea of what life is. It shows that simplification can also be a successful evolutionary strategy. It's not always about getting bigger and more complex.
It definitely blurs the lines in a fascinating, really profound way. And speaking of blurring lines, let's shift gears from the microscopic world of biology to the quantum nature of reality and consciousness. Classical physics, around the turn of the 20th century, famously struggled with phenomena like the ultraviolet catastrophe of black body radiation.
Yeah, predicting infinite energy at high frequencies, which obviously doesn't happen.
Right. And the photoelectric effect, where light intensity didn't increase electron energy, only the number of electrons, and the mystery of bright line spectra, where elements emitted only very specific discrete frequencies of light. It was a real puzzle.
That's where quantum mechanics stepped in, offering a completely new language to describe reality. De Broglie's hypothesis, for instance, suggested that matter itself can travel in waves, beautifully connecting energy, mass, and frequency through equations like EMC2 and ATF. So suddenly, particles like electrons aren't just tiny balls, they have wave-like properties too.
And it gets even wilder when we think about the vacuum. We often imagine empty space as just, well, empty. But quantum mechanics suggests it's more like an elastic, nonlinear medium full of vacuum energy. Is that right?
That's the idea. When light is confined in a box, for instance, it actually gains inertial and gravitational mass, behaving like a solar wind in a way. This leads to the pretty provocative idea that particles might just be some kind of self-confined light.
So out of seemingly empty space, you're saying particles just appear. Does this violate any fundamental laws we thought we knew? Or does it just redefine empty space?
It fundamentally redefines empty space. And this nonlinear behavior of the vacuum is especially evident at what's called the Schwinger limit. At extremely high field values, like those found in gamma radiation, the vacuum can spontaneously create electron-positron pairs out of seemingly nothing. It shows the vacuum isn't just a passive void, it's a dynamic, energetic medium that can literally conjure matter from energy following EMC2.
That's mind-bending. Okay, so if everything is fundamentally a wave, how do we end up perceiving solid particles? Quantum mechanics uses this mathematical construct called a wave function, or CI. What's crucial here is that CI is a complex number, not a real one. Can you explain what a complex number is in this context and why its squared magnitude representing a probability leads to the deeply philosophical concept of wave function collapse upon measurement?
Okay, think of a complex number, not just describing where something is, but also its potential for being in different states at once. It encodes possibilities. It's how quantum mechanics describes potentiality, not just certainty. The wave function describes all the possible states a particle could be in. But the moment we measure it, try to pin it down, that wave function collapses, and we observe just one specific outcome. This transition from a world of probabilities to a single observed reality, well, it's still one of the biggest mysteries. It really hints at the observer's role in shaping what we perceive.
Yeah, and while mathematical operators act on the wave function to give us observable quantities like position or momentum, uncertainty is one of the key concepts in quantum mechanics, famously described by Heisenberg's uncertainty principle. We just can't know everything with perfect precision simultaneously. There's an inherent fuzziness to reality at its most fundamental level.
Exactly. It's built into the fabric of how things work at that scale.
Now, connecting this quantum strangeness to perhaps the greatest mystery of all, consciousness. Let's talk about Federico Faggin, a true pioneer, right? He designed Intel's first microprocessors, the Z80. He grappled with his own hard problem of consciousness. How could profound feelings like love possibly arise from mere electrical signals in the brain, which he initially saw as just a machine like the computers he was building?
Yeah, Fagan had this extraordinary personal awakening experience. He describes being at Lake Tahoe, driven by an intense desire to understand his own unhappiness. And he experienced late one night this beam of physical energy originating from his chest, filled with powerful love, joy, and peace. He said his consciousness felt home within this light. This profound event totally transformed his life, dedicating him to connecting spirituality and physics, seeking a deeper understanding of reality beyond the purely mechanistic view.
That's an incredibly powerful life-altering experience. His belief, stemming from this, is that a deeper reality is inherently quantum, where quantum information is even more fundamental than physics itself. Can you elaborate on what he means by quantum information in this context, and how it moves ontology, the nature of being, to the inner aspect of quantum fields where comprehension, meaning, and experience truly reside?
Well, for Fagan, quantum information isn't just data like bits and bytes, it's the very fabric of meaning and awareness itself. He suggests that consciousness isn't just something that emerges from complex brains like a byproduct. Instead, it's a fundamental intrinsic quality of the universe existing within the quantum fields themselves. Our brains then aren't generating consciousness from scratch, but are more like receptors and processors of this deeper intrinsic quantum information, allowing us to experience it as comprehension, meaning, feeling, and so on.
And this quantum perspective also offers a very nuanced view of free will. For Fagan, it's not about moment-to-moment control, deciding coffee or tea right now, but more a time-extended process of applying consistent effort to shape one's cognitive structure and environment over time. But he also believes that what looks like a random event from the outside, say an electron popping into existence here versus there, is actually a free will decision of the field from the inside.
That sounds contradictory. How can an electron's behavior be a free will decision?
It's a challenging concept, for sure. He's suggesting that at the most fundamental level, there's an inherent agency to reality itself. And what we perceive as quantum randomness, like radioactive decay or where a particle appears, might, from an inside perspective of the quantum field, be the expression of some kind of choice or tendency by these fundamental fields.
Yeah.
It's a way to try and bridge the gap between apparently deterministic or probabilistic physics and our subjective experience of having choice, suggesting that true free will operates at a deeper, more fundamental level than our conscious ego. And this next idea is truly provocative. Fagan suggests that memories are not passive data, but patterns themselves have agency of their own. He's echoing William James's idea that thoughts are thinkers. Think about the caterpillar to butterfly transformation. Memories somehow persist through a complete refactoring of the brain. Not as exact replicas, maybe, but as deep lessons that must be reinterpreted for the new organism. What does it mean for memories to have agency?
It means they're not just inert files stored away in a cabinet. They're active, dynamic patterns that influence and shape our perception and interaction with the world now, like a story being retold. Each retelling or reaccessing of a memory involves a slight reinterpretation, adapting it to the current context, the current you. This suggests all life is fundamentally a sense-making process, a storytelling agent. Our past isn't just something we recall passively. It's actively involved in constructing our present reality. The patterns themselves are active.
That's a lot to take in. Wow. So if consciousness is this deep quantum thing, how do we move beyond personal experience and philosophical ideas to a scientific framework that actually tries to measure it? That's where Giulio Tononi's integrated information theory, or IIT, steps in. It's described as a rigorous axiomatic theory that attempts to define when a system is conscious.
Right. IIT is built on 5 core axioms. Fundamental truths about experience itself. That experience exists intrinsically. It's real for the experiencer. It's structured, has parts and relations. It's specific, one out of many possibilities, differentiation. It's unified, integration feels like one whole. And only one maximum is experienced at any given time, exclusion.
And central to IIT is this measure called phi. It's a dimensionless number that measures a system's irreducibility or integration. Can you explain what irreducibility means for consciousness and how a higher phi value indicates a more conscious system?
Okay, irreducibility means the system's experience cannot be broken down into the experiences of its independent parts without losing something essential. The whole is truly more than the sum of its parts, causally speaking. A higher fidelity indicates a system where the parts are so tightly interconnected and interdependent that they generate a unique, unified experience. An experience that cannot be explained just by looking at the parts in isolation. And this theory makes some fascinating, testable predictions. For one, it posits that consciousness is not an all-or-none phenomenon, but graded, which explains why our consciousness can wax and wane, during deep sleep anesthesia, or even when we're just tired or hungover.
And crucially, IIT predicts that purely feed-forward systems, like most current machine learning algorithms and neural nets, have a phi of 0, meaning they are not conscious, even if they can perfectly mimic intelligent behavior, like passing a Turing test. This fundamentally argues against functionalism, the idea that if an AI acts conscious, it is conscious. So this isn't just philosophy, it has huge implications for the future of AI, right? Why isn't simulation the same as actual consciousness, according to IIT?
According to IIT, it's not about what a system does, its output or behavior, but how it does it. Its internal causal structure. A feed-forward system, even an incredibly complex one, simply processes input to output in a chain. It doesn't have the dense, recurrent, internal causal connections that loop back on themselves in the right way to generate an intrinsic, unified experience from its own perspective. To build conscious AI based on IIT, you'd need to replicate the actual causal effect structure neuromorphically. You'd need to build something with the right kind of integrated feedback loops, not just simulate the behavior. You'd need a system that truly integrates information in a way that generates irreducible experience, which is, frankly, far beyond current capabilities.
So using that logic, why isn't the cerebellum, which has, what, billions of neurons, way more than the cortex, thought to contribute much to consciousness, if consciousness is just about having lots of neurons?
Right. That's a great test case. IIT explains that while the cerebellum is massive and neuron-dense, its internal structure is highly regular and organized in parallel, almost like 2D sheets. It lacks the necessary dense, complex, recurrent 3D network connectivity that you see in the thalamocortical system. That complex interconnectivity is what's required for hi-fi, for high levels of integration. The cerebellum is a processing powerhouse for motor control and coordination, but its architectural layout doesn't support the kind of integrated information needed for subjective experience, according to the theory.
That's a really concrete example that makes the theory much clearer. And there's a practical application of IIT, right? This zap and zip test.
Yes. Using transcranial magnetic stimulation, or TMS, they basically zap the cortex with a magnetic pulse and then zip up the data from EEG recordings to measure the complexity of the brain's response. This yields a value called the Perturbational Complexity Index, or PCI, and studies have shown a high PCI correlates well with being conscious, awake, REM sleep, even in minimally conscious states, while a low PCI indicates unconsciousness, deep sleep, anesthesia, vegetative states. This method has even accurately predicted awakening in some patients who were previously thought to be unresponsive. That's a potential game changer for clinical assessment.
Wow, that really is.
It truly is, and fundamentally this suggests that IIT posits consciousness not as some magical fluke of biology, but as a fundamental property of the universe for any organized system with phi greater than 0. Much like mass or charge or energy, it's intrinsic to any system capable of truly integrating information in the right way.
Moving from consciousness itself to the very architecture of our brains, let's explore neuroplasticity. Historically, our understanding of brain regions was quite limited, wasn't it? Penfield's 1957 map showed only a few basic sensory and motor regions. Even by 1990, knowledge was largely confined to broad areas for language or face recognition. We sort of thought of the brain as pretty much fixed, like a hardware diagram you couldn't really change.
Yeah, but the modern view, largely thanks to technologies like fMRI, reveals that the brain contains highly specialized components for specific mental functions. Things like face recognition, a specific visual word form area for reading, areas for processing speech sounds, language comprehension, and even regions dedicated to theory of mind, figuring out what others are thinking.
But it's important to clarify, right? While these regions are functionally specific, meaning they're selectively engaged in one process over others, it doesn't mean they're anatomically specific as the only region involved, or that they're purely innate. For example, that visual word form area isn't present at birth. It develops specifically with the experience of learning to read. It's shaped by what we do.
Absolutely. Experience shapes function. That said, not all brain regions are highly specialized. John Duncan's work highlights these multiple demand regions, mainly in the parietal and frontal lobes. These areas seem to activate for almost any difficult task, whether it's perceptual or high-level cognitive thinking. These regions are believed to be the seat of G. Spearman's general intelligence factor, and patient studies seem to back this up. Damage to these multiple demand areas specifically tends to reduce overall IQ, whereas damage to more specialized areas might cause other specific deficits, but not necessarily lower general IQ in the same way.
This brings us squarely to neuroplasticity itself. The brain's incredible ability to alter brain function in response to experience, shaping how we think and act through actual physical changes in neural circuits. We all kind of know about critical periods, especially in childhood when the brain is highly plastic, super adaptable, and these periods naturally dampen with age. It gets harder to learn languages, for example. But fascinatingly, these windows of high plasticity can apparently be reopened. How?
Well, several ways. By injury, unfortunately, the brain tries to rewire. But also pharmacologically, certain drugs like amphetamines, some antidepressants, or even psychedelics like MDMA seem to enhance plasticity, or through direct brain stimulation techniques.
What does it mean for these periods to reopen? Does it mean an adult brain can become like a child's brain again, temporarily?
In a sense, yes. It means the brain's capacity for fundamental change, for significant rewiring, becomes enhanced for a time. This has really significant implications for rehabilitation. Experts are advocating for much earlier and more intense doses of rehabilitation, really throwing the kitchen sink at conditions like stroke recovery, drawing parallels to how quickly children learn languages or motor skills during their natural critical periods. It's about capitalizing on those heightened states of plasticity when they can be induced.
And brain stimulation is already being used in practice, isn't it? Transcranial magnetic stimulation, TMS. You mentioned Stanford's SYNC treatment for severe depression, using fMRI for personalized targeting of TMS pulses, and achieving incredibly high remission rates in trials. That's amazing.
It is remarkable, and it's also being explored for performance enhancement. There have been studies with ski jumpers, professional football players trying to use TMS to accelerate skill acquisition or boost focus.
Yeah, it's almost like something out of a science fiction movie. Plug in and learn Kung Fu.
Yeah, well, not quite. There's definitely a quick fix desire for drugs or technology to instantly enhance abilities. But it's really crucial to remember that these interventions seem most effective when combined with thoughtful practice and immersive experiences. You still have to put in the work. The stimulation or drug might make the brain more receptive to learning, but the learning itself still requires effort and engagement. It's not a magic pill, but maybe a booster for focused effort.
And there are serious risks to consider, aren't there? Reopening critical periods also creates windows of vulnerability, where prolonged plasticity, if not guided properly, could actually lead to damage, or maybe embedding negative patterns or maladaptive changes.
That's a very real concern. These are powerful interventions. There's an enormous pull for this kind of technology. You can see the appeal. But there are also huge pitfalls due to consumer expectations potentially bordering on, the matrix idea. There's a huge responsibility for researchers and clinicians to clearly communicate what this technology can and cannot do, manage expectations, and ensure safety.
Absolutely. The brain's incredible capacity for change is a powerful tool. But like any powerful tool, it needs to be wielded with great care and understanding.
Exactly. The promise is immense, but so are the responsibilities that come with it.
Wow. We've covered a huge amount of ground today. From the unexpected mechanics of our own bodies with biotensigrity to the mysterious origins of life and things like suchanarchium, and the quantum depths of reality and consciousness, plus the brain's amazing ability to change itself. It's really clear that the world we inhabit and our place within it is far more complex, interconnected, and dynamic than conventional wisdom often suggests.
Indeed. From the smallest biological entities challenging our very definitions of life, to the possibility that the fabric of space isn't empty but a dynamic medium, to particles being self-confined light and our own brains being these incredibly dynamic, adaptable structures shaped by experience, it's all interconnected in a way that truly redefines what we thought we knew. It's quite humbling, really.
So what does this all mean for you as you go about your day? If consciousness might indeed be a fundamental property of the universe, not just an emergent trick of the brain, and our memories are not passive data, but active agents shaping our reality right now, what does that imply for our understanding of ourselves as individuals and our seemingly small place in this vast cosmos? These are definitely questions that will keep us all deep diving for a long, long time to come.